This video lecture is about the dying stages of high-mass stars, which are more than 8 solar masses. Their birth and adult stages are essentially the same as for the low-mass stars, just doing them more quickly. While low-mass stars have lifetimes measured in hundreds of millions to hundreds of billions of years, the high-mass stars live at most several million years. Recall that the high-mass stars are very rare in the universe, with most stars being less massive than the Sun. So what is described in this lecture is extraordinary and rare. However, the basic stages are the same: red giant, outer layers ejected, and core remnant. But the high-mass stars will cycle between red giant, supergiant, and core fusion several times, and the final mass loss is a powerful supernova instead of a gentler planetary nebula. And the core remnant neutron star or black hole is more massive, but much smaller than a white dwarf. The following 21 slides step you through the dying stages of the high-mass stars. The captions describe what's going on. The sequence starts off the same as for the low-mass stars, but you'll see that the high-mass star is able to cycle many times through the core fusion stage as ever more massive nuclei are built up at the core, on up to iron. Also remember that even when the star becomes supergiant in size, it will have less mass than it did during the main sequence stage. Stars lose mass as they live out their lives. At the end of the main sequence stage, the nuclear fusion fuel runs out in the core. The core contracts and heats up. The shell layer outside of the contracting core begins fusion. The increased energy from the center pushes out the outer layers. The massive stars will be able to reestablish core fusion each time by getting even hotter and denser than before. Each core fusion segment occurs in a shorter and shorter time span. Until it fuses silicon to make iron at several billion degrees in the last year of its life. Iron is the end stage because the star does not gain energy when fusing iron, so the red giant core fusion cycle ends when iron fills up the core. In this next to last stage of a star's life, the outer layers are ejected explosively as the core shrinks to its most compact state as a neutron star or black hole. A large amount of mass is lost at this stage as the outer layers are returned to the interstellar medium. The explosion is the result of the massive star's core suddenly collapsing to form the super-hard neutron star, the size of a city, as the protons and electrons are fused together violently, and the outer layers rebound off the very stiff core. When the neutron star is produced, a huge number of neutrinos are also produced. Enough of this huge number of neutrinos interact with the gas in the outer layers, helping to heat them up. During the supernova outburst, elements heavier than iron are produced as free neutrons produced in the explosion rapidly combine with heavy nuclei to produce heavier and very rare nuclei like gold, platinum, uranium, and others. This happens in about the first 15 minutes of the supernova. A very massive star's core may temporarily form a neutron star for the explosion to happen before it continues collapsing to become a black hole, or a black hole may form without the supernova. We aren't sure. Next slide. The neutrinos, not neutrons, but neutrinos, formed when the neutron star core is created, fly away from the stiff core, carrying away over 99% of the energy from the core, collapse with them. Less than 1% of the energy goes into kinetic energy, driving the gas envelope outward. Less than 0.01% of the energy goes into making photons, but that tiny fraction of the energy in the form of photons is as bright as 100 billion suns. That's as bright as an entire galaxy. Next slide. When the high-mass star was in the red giant core fusion cycle, it was making ever heavier chemical elements on up to iron. During the supernova, the temperatures and densities are so tremendous that during the few minutes of the core collapse, the iron barrier is overcome and even heavier elements are created, such as copper, nickel, silver, lead, uranium, etc. All of these chemical elements are thrown outward to be used later in making planets, moons, life, and others. The statement at the bottom of the slide is how we're directly connected to the cosmos. All of the atoms on the Earth, except hydrogen and most of the helium, are recycled material. They were not created on the Earth. They were created in the stars. Through the process of nuclear fusion, stars make new atoms, new elements. Chemical reactions do not make new atoms. They just rearrange the atoms. Supernova are the primary agent for dispersing the elements heavier than helium to other parts of the galaxy. So in order to create a rock-iron world like the Earth and life, you need previous generations of stars going supernova and sprinkling other gas clouds with their debris. Next slide. For cores between 1.4 and 3 solar masses, the core collapses to form a neutron star. The electrons and protons fuse together to make neutrons, and it is the neutrons that run out of room to move and hold up the dead star against any further collapse. Many young neutron stars will produce beams of light out of their magnetic poles to make what's called a pulsar that lights up the surrounding gas nebula, such as the Crab Nebula shown here. Next slide. A pulsar is a rapidly rotating, spinning neutron star with a very strong magnetic field. The magnetic field is so powerful that it can strip charges off the neutron star's surface, and these charged particles spiral around the magnetic poles to produce beams of light. Next slide. If the beam or beams of light cross the Earth, you will see the pulsar flashing on and off very quickly. So pulsars pulsate by spinning, not by changing their size and temperature. Most pulsars produce light in just the radio band, but a few, like the Crab pulsar here, also pulsate in the optical and X-ray bands. This animation of the Crab pulsar has been slowed down a lot. It spins 30 times a second. Next slide. This slide describes why neutron stars spin so fast. A property of a spinning object is the angular momentum, which is the mass multiplied by the spin speed multiplied by the radius. The mass remains constant. In order to keep the angular momentum constant, the spin speed must increase if the radius decreases. This will keep the product of spin speed times radius the same value. A slowly rotating red giant star will have the same angular momentum when it becomes a tiny, fast-rotating neutron star. The same thing happens when a spinning ice skater pulls in his or her arms and legs in order to spin very fast. The magnetic field is the relic magnetic field from the star's previous life stages. The magnetic field is frozen into the star, so when the core collapses, the magnetic field is compressed too. The magnetic field becomes very concentrated and much stronger than before. The energy of the beam comes from the spin energy of the pulsar. So as the light is emitted from the pulsar, the spin energy of the pulsar decreases and the neutron star slows down. The angular momentum does get slowly robbed by the escaping light. When the neutron star slows down to spin rates of several seconds per turn, the pulsar phase shuts off. However, this happens over a very long time, and we have to use atomic clocks to notice the slight slowdown of pulsars. Next slide. This slide shows the size of a typical neutron star, about the size of a city. Recall that a white dwarf is about the size of the Earth. A neutron star has between 1.4 and 3 solar masses of material shrunk down to the size of a city, so they are incredibly dense. 1 teaspoon of neutron star material would have a mass equal to all of humanity, or a large mountain. a mountain per teaspoonful. This graphic shows the 3 core remnants possible with the neutron star in the middle. Note that masses given here are for just the core masses, only after all of the outer layers have been ejected. The electrons and protons combine to form neutrons, and neutrons can be packed much closer together than electrons. The neutron star is like a city-sized atomic nucleus. If the core mass is greater than 3 solar masses, even the overcrowded neutrons can't hold up the star, and gravity finally wins. Nothing we know of can prevent the total collapse of the core. The star becomes a region of pure gravity, a black hole.